Hello and welcome to our algebra recording for week 16. We are about 2.5 weeks out from the end of the semester, so that is exciting, and I want to keep reminding you guys of how close we're getting. So if you've got a goal grade in mind, you are working to achieve that goal. Remember, I'm only taking redos from our current unit, which is Unit 4. So if you're working on getting your grade up, one thing that you can be doing is redoing low-scoring assignments. At this time, I do want to make sure you've got your math notebook out, and we are going to start with a review question about exponential functions, which has been our focus for the past few weeks. So I've got an exponential function written below, f of x equals 24 times 0.45 to the x. What I would like for you to do is answer a couple of questions based on this exponential function. So first, is this exponential function below showing growth or decay? And then once you choose your response, how do you know it's either growth or how do you know it's decay? And then I would like you to follow up by telling me what is the initial amount in this exponential function. So go ahead and click pause and try working through this on your own, and then when you're ready to check your work with mine, go ahead and click play. Alrighty, so if you think back to what we've been studying the past couple weeks, it's all been exponential functions. And we learned that exponential functions are in this format where we've got f of x equals, I'm typing or writing up at the top here because I don't have enough room at the bottom, a times b to the x power. So the a variable, or the a term, always represents our initial amount. Always represents our initial amount. Where the b, the number that's being multiplied by x, to the x power, I should say, not being multiplied by x, being multiplied to the x power. The b represents our multiplier, if you will, and it will let us know if we've got growth or decay. If it's growth, that b term is going to be greater than 0. This term right here would be greater than 0. If it's decay, that term is going to be greater than 1, but also that b term is going to be, oh, I should have said less than 0. So let me just erase. All right, so I accidentally erased everything and had to re-put it up, so it might look a little different. But so going back to this b term, this being raised to the x power. So if it's growth, that b term is going to be greater than 1. If it's decay, this term b will be represented by a number that is less than 1 but greater than 0. It might be a decimal in that case. So coming back down and looking at our original function, this term right here, our b term is going to be what represents growth or decay. So that's this number right here, that 0.45. And since it's less than 1 but greater than 0, it's showing us that we have decay. We have decay, and we know that because that b term is less than 1 but greater than 0, and that's how we know it's showing decay. What is the initial amount? Well, remember, that's our number a that's represented by a being multiplied by b. So right here, this 24 represents the initial amount. So the initial amount is going to be 24. So that is it for our warm-up. I'm going to move on to the next slide, so if you need more time, go ahead and click pause. So on to the next slide. Another reminder, I already said this, but in writing, the last day of the semester is about 2 weeks away, so just keep that in mind, what we chatted about already. This week, we are going to look at compound interest, and then we're going to move on to writing exponential function rules from a table, which is a majority of what this recording is focusing on today. And then lastly, you're going to look at Unit 4, Session 8, which is linear and nonlinear rates of change. So we are in the last unit of this semester. Just to let you know, we will be ending with Unit 4 this semester. I wanted to review exponential functions, but we really already did that in the warm-up. So really what I wanted to do was point out the different parts of an exponential function and what we can tell from an exponential function and what they look like in an equation form. So f of x equals, we're always going to have a number times another number that is being raised to the x power. And we chatted about what these represent, but really quick, let's do a review. So the a term is always going to represent the initial amount. Write this down in your math notebook. The b term is always going to represent the multiplier. Because remember, when we look at a table and we're focusing on the x and y terms, the y terms are always going to be multiplied by the same amount. And that tells us that something is exponential because it's being multiplied by the same amount each time. It's growing at a constant rate because it's being multiplied by that same amount each time. And that multiplier is represented by this term b. That represents our multiplier. It also lets us know if we have exponential growth or decay. If you haven't written this down in your notebook already, please do. So growth, remember b can never be equal to 0, or I'm sorry, 1, I meant to say. A can never be equal to 0. That's what I was trying to say there. B can never be equal to 1. If it's growth, that b term is going to be greater than 1. If it's decay, that b term is going to be less than 1 but greater than 0. So just a quick reminder of what exponential functions look like and all the important parts and what each term represents. I'm going to move on to the next slide, so if you need more time here, go ahead and click pause. All right, so we can determine the type of growth by looking at a table. We've done this a little bit in the past already, but let's review. So linear growth, remember linear functions, when we graph them, they are going to be a straight line. We can increase, we can decrease, but linear functions, when we graph them, we will get a straight line. Whereas exponential functions, when we graph exponential functions, we're not going to get a straight line anymore. We're either going to get a shape like this, or it's going to look like this. So this one shows exponential growth, where this one shows exponential decay. So let's look back at our tables. And first, let's look at this table here on the left. And I'm looking at my x values, and my x values are increasing by 1 each time. They're increasing by 1 each time. That's a good thing. So now we can come over here and look at the outputs, or the f of x values. You can look at them as the y values or the outputs. So remember, these are always your inputs, your x values, and then we always get our outputs. So let's look at the function outputs and see if there's a pattern. So when we go from 6 to 8, it looks like we're increasing, right? And it looks like if I add 2, I get from 6 to 8. Does that pattern continue? If I go from 8 to 10, I'm also adding 2. And then that pattern continues. So here we're adding 2 each time. And since we're adding a certain amount, that means we've got linear growth. And if we were to graph this, we would get that straight line. Now let's look at exponential growth. So again, looking at our inputs versus our outputs. And our inputs were increasing by 1 each time. That's a good thing. So now let's compare the outputs each time. So from 2 to 6, it looks like we're going up, we're increasing by 4, right? So plus 4. What about from 6 to 18? Uh-oh, we're not adding 4 anymore. So let's go back and rethink the pattern that we have here. So what's another way we can go from 2 to 6? Well, what about multiplying? So 2 times what equals 6? I know 2 times 3 equals 6. Does that same pattern occur from 6 to 18? Does 6 times 3 give us 18? It does. And guess what? That same pattern keeps continuing here. So because we're multiplying by the same amount each time, that means that we've got exponential growth. Oops, we're multiplying. That looked like a plus at the bottom there. So the difference between exponential growth and linear growth is the amount that we're increasing with our outputs in time each time. So if we're adding or subtracting by a certain amount, we're going to have linear growth. Where if we're multiplying or dividing by a certain amount each time, or really we could just go with multiplying, because if we're getting smaller, we could say we're multiplying by a fraction, right? So if we go from 10 to 5, we would be multiplying times 0.5. So really, we're multiplying by a certain amount each time. We're multiplying by a certain amount each time. So get away from the division. Let's think of it as only multiplying. And when we're decreasing the amount each time, we're going to be multiplying by a fraction to show that. So again, just wanted to look at how we can determine linear growth versus exponential growth from tables. So I'm going to go on to the next slide. So if you need more time, go ahead and click pause. So now, how can we write the function for exponential growth when we're looking at a table? So we're going to look at how we can go from a table and come up with the exponential function. So first, we want to determine if we do in fact have an exponential growth. So what we're going to do is make sure our x values are increasing by 1 each time, and they are. And then we're going to, so step 1, determine if we have exponential growth. So now we need to focus on the outputs, right? Our f of x values, our outputs, and how much are they increasing each time? Well, this is the same one from the previous slide. So we're multiplying by 3. We've already done this. This is the same slide from the previous slide. So we are multiplying, so we say yes, and because we're multiplying times 3 each time. So we've determined this is an exponential function of some sort because we're multiplying by 3 each time. So now we know that, let's figure out, remember the exponential function is always a times b to the x power. So let's now find the a value, or the a value, a term. So what is the a value? So remember, the a value always represents the initial amount, right? The initial amount. I could have written this down here. Let's make it bigger. So I wrote it down here. It's bigger. So a is the initial amount, and the a value is going to be the initial amount. So we're looking to see what is the f of x value when x equals 0, because that's the initial amount. So we want to see what is the f of x value when x equals 0. That's the initial amount. So we look here, when x is 0, the f of x is 6. So f of x, when it's 0, it is going to be equal to 6. So that means the a term in our function will be equal to 6. All right, so we found the a, the initial amount. In this case, it's going to be 6. So we're working on writing that function out. Now, what's the b value? Oops, we forgot to put the x there. The b value, remember, is the multiplier. It's the amount that we're growing or decaying. And in this case, stopping here, I'm putting in step 3, finding the b value or the multiplier. And we already did that in step 1, right? When we determined this was exponential growth, we determined that by seeing that it was the y values, the outputs were being multiplied. They were increasing our rate of being multiplied by 3 each time. So the b value, or our multiplier here, is going to be that b equals 3. So now we can really plug everything in and find our final equation. So we weren't quite done. Now we are done. So let's write in our final equation. So it's going to be f of x equals 6 times our multiplier, which is 3 raised to the x power. And I just cleaned up this equation over here and reminded us what the a term and the b term mean, and then our steps of how we found each of those. So that is how you go from a table to writing the function that represents that table. So I'm going to go on to the next slide. So if you need more time, go ahead and click pause. So let's try another one. So take a look at this table, and if you want to, try this on your own first. So we're trying to write the function. So remember, f of x equals a times b to the x. So if you want, go ahead and see if you can write this on your own now. Go ahead and click pause, and then when you're ready, you can check your work with mine. So first, does this represent an exponential function? So we see that we're adding 1 each time on our x values. That's good. So now we can look over at the outputs. So how do we go from 0.125 to 1? That's kind of tough. So what I'm going to do is I'm going to focus on these whole numbers here and see if I see a pattern, and then I'll check it going from 0.125 to 1. So from 1 to 8, what are we multiplying times? Times 8, right? And then 8 to 64 times 8. 8 times 8. So each time we're multiplying times 8. I'm going to change the font color here. That was a little hard to see. So what I'm pulling is first I know that this is an exponential function. And then, so yes, it's exponential. Showing exponential. And its multiplier is 8, right? So that means that our b term has to be 8. Second step, what is our a term, or the initial amount? What is the initial amount? Oh, by the way, if I were to check this, 1.125 times 8 does equal 1. I forgot to put that in there. So the initial amount, that's going to be our a value. So what is the initial amount? And that occurs when x equals 0. What is the corresponding output? And that value is 8. So when x equals 0, the output is 8. So that's the initial amount. That's our initial amount. Now we can write our equation. We're done. F of x equals, our a value is 8. Our b value is also 8, and we're raised to the x power. So lots of 8s there. Okay. I'm going to go on to the next slide, so if you need more time, go ahead and click pause. One more to try, and in this case, we're getting smaller each time. So again, as I mentioned, when we're talking about how we're going from each value to the next value, I don't want you to say we're being divided by. I always want to find a multiple. Always find a multiple. So if we're getting smaller, or I shouldn't say a multiple, what's being multiplied each time. So if we're getting smaller, which means we've got decay, then look for a fraction or a decimal. So focus on a decimal or fraction that helps us determine how we go from one of our outputs to the next output. So again, don't come up with a division because that won't work. That won't get us the right equation. We need to find always what's being multiplied. So, and if it's getting smaller, we'll just use a fraction or a decimal to go from one value and make it smaller each time. So and another quick way, an easy way to do that is take one of our values and divide it by the previous number, and that's going to be your multiple. That's going to be your multiple, the number that we would use. So for example, how do I go from 125 to 25? Well, if I take 25 and divide it by 125, what do I get? So 25 divided by 125, when I type that into my calculator, I get 0.2. That's your multiple. So if we were to take 125 and multiply that by 0.25, guess what you get? You get 25. So what we're multiplying each time is going to be 0.2. So again, if it's hard for you to see what that fraction is or the decimal that we're using to go from a larger number to a smaller number, take any of the numbers and divide it by the previous one. So we could have done 0.2 divided by 1. Take this number and divide it by that. Equals 0.2. That's your multiple. So we have determined that our B value, our multiple, is going to be 0.2. What is our initial value, or the A value in this case? Our A value, remember, is our initial value, and that's always going to occur when x equals 0. So when x equals 0, the output is equal to 5. So that's our initial amount, is 5. Now we can quickly put that into our equation. F of x equals 5 times 0.2 to the x. And we're done. So not too tough, right? And you're going to get a lot of practice with that this week. I'm going to go on to the next slide, so if you need more time, go ahead and click pause. I'm going to put up the key phrase assignment. So today's recording really focused on going from a table and writing an exponential rule, or that exponential function that represents that table. And we learned that that A value in f of x equals a times b to the x, that A term represents the initial amount. So when writing an exponential rule from a table, how do you find or identify the initial amount? And that is your question that you need to answer to get your credit for watching this week's recording. Have a great rest of the week, and if you need help with anything, do not hesitate to ask.